Hello, welcome all. We are in the chapter 12 of limit state of serviceability. I hope from the beginning we have seen limit state of collapse, how to design a beam, how to design a singly reinforced, doubly reinforced beams, and how to design a flanged beams and analyze those beams. And with extra care about shear and bond, everything we have seen. So this chapter will also come under beams and slabs. Okay, but in this case we are going to check the serviceability conditions. We are not going to design for the strength. Okay, so totally different story. Limit state of collapse is we are going to design a structure for a bending, shear, or something like for torsion. That is for designing for a collapse. Is somebody going to collapse you by their strength? We are going to do that, but we cannot keep on designing a beam like very high depth and very high concrete and AST of 1500 mm square or 2000 mm square. We are keep on increasing the reinforcement and make it like a very rigid beam, correct? Then but its purpose should be there. Okay, the purpose of the beam should not hindrance to the other structures. Like if you are keep on increasing the depth is very good, so if you are increasing the depth you can take more moment, but if you are keep on increasing the depth it will come hindrance to the window and all to the wall. So there are some serviceability condition we should verify in that case. So in working chess method we will never do a serviceability check, we will have a general check for serviceability. In limit state we have to do some serviceability checks. What are the different serviceability checks? Deflection. So as I told you, the main concern is a deflection. How much maximum deflection we can allow for a beam, slab or anything. How much maximum deflection you can allow. You can allow some deflection because we are designing the total structure as a elastic structures. Okay, so we are not designing as a plastic structure which will reach the cracks immediately, and we are not considering the RCC concrete as a brittle structure that only crack will penetrate. We are assuming everything as a, we are going to design the structure as a under reinforced section. So the under reinforced section always there will be a ductile behavior will be there. So there will be a confirm there will be a deflection. Okay, when the load is applied. So up to how much deflection we can allow. That is the first check we will do. The cracks. Second check is crack. I think we have discussed crack in chapter 2 or chapter 3. So the crack with it is in annexure in your IS 456. Mostly in our undergraduate courses, the syllabus is not framed for designing the crack width. The crack width is very important concern in the designing of water tank, designing of nuclear power plant everywhere, where the small minute crack of less than even 0.3 mm will penetrate the water or anything, the oil or petroleum, anything can penetrate inside, and then it will create a hindrance to the reinforcement, or it can come out, or it could have been disaster. So very peculiar structures, even for the port and harbor structures we will do the crack width checks for the pile foundation, because the most portion of the pile above the seabed will be exposed to the seawater. So the seawater will be coming and splashing every time, splashing the pile. So when the crack width is very small, crack width is there, the water can penetrate inside and it will corrode the reinforcement. So the crack width check will is another serviceability check, which is not concerned about your design, right? Which is not concerned about your strength, whatever be the bending moment, whatever be the shear force torsion, anything can happen, but the crack width will change the total design. Okay, so that crack width you will study in your masters or higher degrees if you are going to do your masters, or if you have more interest you can check the annexure, I think G or E, I didn't remember. You can check that crack width, how to check the crack width for any type of structure. Okay, so next thing is vibration. Obviously this is a dynamics. Okay, so far whatever we are studying in bending moment, 200 will act, shear force this much will act. So we have seen so many examples, around 40-45 examples we have seen. In all the examples we have given a load that is standing there, no load is moving, there is no moving load at all, correct? The bending moment simply is about beam acting with a point load at the center. So we have discussed all the loads based on what the structure, the bending moment is acting at the center of the sorry was the load will be acting at the center of the beam. So there is no, the load is not dancing at all, the load is not moving anywhere. So we are concerned about, so far throughout the studies we have did for static load, we never considered about dynamic load. Whenever the load is dynamic, the deformation will be dynamic, the structure will vibrate. When there is an earthquake load, the structure will vibrate. When there is a wave load, your structure will oscillate with its fundamental vibration. So this, all these serviceability conditions will come under chapter you will study in your master's degree. Okay, master's course we will how to design a structure for a vibration. Okay, so next thing is fire resistance. So fire resistance, hopefully after this incident of that helicopter sorry, the aeroplane crashing in the world tower in US in I think around 2000 first half. So after that incident, all the code book has been revised to include design the structure for the fire resistance, because the building was collapsed. The two buildings collapsed only because of the fire. You can Google and you can study as per the technical lectures. What I have learned, the structures, the steel, the structure is mainly steel. The steel, when the aeroplane bursted, the temperature created by the explosion was very high. It's so higher than the melting point of the steel. So the steel columns, everything got melted, so the total structure collapsed in straight. Okay, you can see that videos. After that incident, all the throughout the world, all the code book has been revised to include a section for fire resistance. Okay, so that one, and the durability check, how long your structure should be durable. These are the serviceability checks you should do, depends on your concern. And mostly, if deflection, if you are making the deflection under control, all other factors will be under coming control. And we will see more about the exam point of view. So we will concern more about the deflection. Okay, so the total deflection can be two types: short term deflection or long term deflection. Short term deflection is nothing but if I am walking over the beam, the deflection will be temporary, right? So the temporary, I am moving out, I won't be standing for a long time, so that is temporary or elastic deflection. Long term deflection is permanent. Yeah, it will be there for a long time. That is because of two cases: creep and shrinkage. Creep deflection is because of a constant load. When you are applying a constant load over a beam, like when you are having a building, consider you are having a water tank at the top. Okay, so the water tank load is a constant. When you're I'll give you a little more example for the creep. So consider you are a weightlifter. Okay, so you will able to lift a weight of 100 kg. So I have lifted a weight of 100 kg. Okay, very good, everybody clapped. How long you can keep the 100 kg in your hand? You lifted position 10 seconds, 20 seconds, 15 seconds. You cannot keep it for 1 month, right? So the load, you were able to lift the load at initial stages, but when the time progresses, the load becomes very heavy because of the gravity pull, and you have to put the load down. Correct? So that is the creep load. When you are constructing a water tank above the building, everything looks good, no problem at all. After 1 month, after 1 year, you see the cracks below the water tank in the top. In most of the buildings, because of the heavy load through the time. Okay, the crack developed because there was a deformation. That deformation is called creep deformation. And similarly, shrinkage is I hope you know what is shrinkage. Shrinkage is because of the shrinking of concrete after putting a concrete. You will cure it for I think 14 to 21 days for most of the structures, and 21 days we will see for cube. But for residential buildings, we will not wait for 28 days. We will do 14 to 21 days, depends on slab or a column or anything. So shrinkage will have a deflection. Okay, when when the concrete is shrinking, there will be a heavy deflection. That is a permanent deflection, right? So this is another two types of permanent deflection. Okay, so I told you little bit details already, but I will come to the short term deflection. Short term deflection is an elastic deflection. Whenever there is an elastic theory, we will go to Euler. Hooke's law, sorry, we will go to the Hooke's law. Stress is directly proportional to strain within the elastic limit, right? So in that we will take out the directly proportional with a constant called Young's modulus. Young's modulus is nothing but 5000 root of FCK as per IS 456. Okay, so Young's modulus of a concrete is directly connected with your FCK. If you are using M20, different Young's modulus, M30 different Young's modulus. Okay, M40 different Young's modulus. So the creep and shrinkage I have given details here already. So these are those deflections. But you cannot use the short term Young's modulus, which was I have shown earlier, 5000 root of FCK, that we cannot use for a long term Young's modulus, because creep will happen maybe after 1 year or 2 years. So this, for that long term Young's modulus, depends on a formula called EC by 1 plus theta. So we will divide the 5000. We won't get the 5000 root of FCK. We will get higher. 1 plus theta. Depends on the theta value. Theta value is 2.2, 1.6. If you are calculating the long term exponents after 7 days, the creep will be higher, and it will become constant, right? After a certain time, you won't have more creep. Creep will reach its ultimate limit, and it will be a constant. After 1 year, 1.1. So depends on the theta value. You substitute the theta value from the table. Substitute here, you will get the long term Young's modulus. Okay. So these maybe they will ask you for 1 mark related to long term Young's modulus. Okay. So next point is deflection limit. Okay, how much maximum deflection you can allow for a total deflection? Because of short means, like I told you, like elastic deflection and long term deflection. As overall, nowhere you should not allow the deflection to cross span by 250. Overall, whether it is a temporary or permanent, span length divided by 250, it should never cross a span length divided by 250. But deflection due to live load plus creep and shrinkage means after the structure is ready, not because of dead load, not because of partitions or portions or finishing. So the deflection due to live load plus creep and shrinkage, that will happen after the construction, right? So how much deflection you can allow after the construction? That deflection should not be greater than span by 350 or 20 mm. Okay, you should remember these 2 points also. Maybe they will ask for another 1 marks somewhere. Okay, so span by 250. I hope you know what is span length, right? It is the I think I showed you in the chapter 3 or something. It is the distance between center to center distance between the column for a beam, or L by D. I think we have noted for cantilever beam. Okay, we will see one example how to calculate this span. Okay, so now I have given a limit, but how to check for a deflection? How will you calculate the deflection, or how to determine the depth based on serviceability? This is very important matter, because you know how to design the depth for singly reinforced based on the strength, right? I hope you know the formula ME equal to 0.36 FCK BD square per D minus 1. From that you will can find the determine the depth value. I think we have even solved 3 or 4 problems in how to find the depth value. So based on serviceability condition, how to determine the depth? So they have given a formula in IS 456. Span by depth ratio should not be greater than for a beam or one-way slab. Okay, for beam on one-way slab, span by depth ratio should not be greater than K1, K2, K3 into P. Okay, so what is P? P is the permissible value. For a span less than 10 meter, P is chosen as, so you can see the members I have given: cantilever beam, simply supported beam, fixed or continuous beam. If the span length is less than 10 meter, for cantilever 7, simply supported beam 20, span by depth ratio is 20, fixed or continuous beam it is 26. For the span length is greater than 10 meter, they have given for cantilever you cannot have span more than 10 meters. So they didn't give any value. For simply supported beam 20, that span by depth ratio of 10 meter, the 20 value into 10 meter divided by the span length. Okay, so that will be the another ratio. For fixed or continuous, 26 into 10 by span. This is the P value. The table I have shown here is the P value. Okay, so I told you this P is the permission value. But what is the K1, K2, K3? K1 is the modification factor. All K1, K2, K3 is a modification factor. K1 is the modification factor for, first I will go here, then I will show you here. K1 is the modification factor for, it's a function of AST, area of steel, tensile steel reinforcement. Okay, if AST is very high, percentage of steel will be very high. If percentage of steel is very high, you can go to this graph. You can see this one, left side graph figure for I took it from IS 456. You can see when the percentage of reinforcement is going higher in x-axis, K1 value is coming down. Okay, similarly the next figure is for K2. K2 is a modification factor as a function of ASC, area of steel in the compression side for the beam. Okay, so when the ASC is getting higher, K2 value is getting higher. You can see x-axis, this curve is increasing. But in figure 4, when AST is increasing, K1 is coming down. Okay, so okay, so I told you AST is increasing, K1 is decreasing, then the P value will obviously come down when you are multiplying that. So the actual deflection will be very high. Okay, similarly for K2 factor, AST is increasing, K2 will increase. If K2 is increasing, P is increasing, then the deflection will be coming down. This is very important point, because when area of steel in compression side, if you are putting more reinforcement at the top, so the shrinkage deflection will be very less, because in compression only we are considering the concrete, correct? So in the when the concrete only will able to shrink. So when you are having more ASC, area of steel in compression, the K2 value will be very high, so that the very less deflection will happen. The K3 value is a factor for flanger beams. It's for flanger beams. For BW by BF ratio, width of the web by flange width ratio, if it is very high, K3 value will be very high. If K3 will be very high, P will be very high, and the deflection will come down. Okay, so most of the problems they will give you the K1, K2, K3 in the problem itself. So you can directly substitute in that formula and find the L by D ratio. Okay, so I have given one example, notable cross sections. Okay, what the notable cross section is, as I told you, if you have more reinforcement at the top, it is very good. So very less shrinkage deflection will happen. Overall, as a overall, doubly reinforced flanger beam is the top class beam in terms of both limit state of collapse and limit state of serviceability, and that's what we are providing everywhere in our residential buildings across India. Okay, So that's what, right? Because we have a slab at the top, we have a reinforcement at the bottom. Okay, clubbing both will be looking like a doubly reinforced flanger beam. Okay, that's the figure I have shown on the right side. Okay, so if it is a two-way slab, because the previous formula I showed you is for one-way slab or a beam. For a two-way slab, what is two-way slab? The span length LY by LX should be lesser than or equal to 2. It should be span length ratio should be lesser than or equal to 2. Also, if live load is less than 3 kN per meter square and the span length is less than 3.5 meter, then span by depth ratio should be lesser than or equal to P. Okay, span by depth ratio should be lesser than or equal to P. So, what is the P value? Again, permissible value. That ratio is given here 35-40. Initially, we have seen 7, 20, 26 in one-way slab or beam. Here it is 35 or 40 for a mild steel bars, 0.8 into 35, 0.8 into 40 for HOSD bars. If the span length is more than that, if the span length of your two-way slab is more than the 3.5 meter, then use the same ratio what we have given for a one-way slab. Okay, so this is another table you should memorize for span by depth ratio for two-way slabs. Okay, so I will solve some 2-3 problems. I will show you how to use these formulas. Question: a simply supported beam of effective span, the beam is there 4 meter span length, minimum deflection with modification factor they have given K1, K2, 3 they have given. Unless they didn't give, take the other factor as 1. Okay, then what is the depth? That's what they asked. It's very simple. So we know the formula for some beam. Span by depth ratio should be greater than K1, K2, K3 into P. They have given K1 1.1, K2 1.2 and K3 they didn't give, take it as a 1. Permissible value for simply supported beam and the span length is only 4 meter. So the span by depth ratio is 20. You can, if you have passed the video and note the table values, you would have known that is 20. So span length is 4000. You put everything, you will get the depth as 150 mm. So for 4 meter beam, the depth required for serviceability is only 150 mm. Obviously, nobody will put 150 mm. It will be at least 200, 300, 400 depth. So the requirement is only 150. So if you have provided higher, then obviously it is very good. It can take more deflection. Deflection is under control. Okay. So next question: what is the minimum effective depth of reinforced concrete beam of 15 meter span? The span is very high. That initially it was 4 meter. It's 15 meter span. So again, L by D should not be greater than K1, K2, K3 into P. So L, I am taking it as a meter itself. So 15 by D should be lesser than or equal to. So K1, K2, K3 they didn't give. So 1 into 1 into 1. And P value, permissible value, since the span length is more than 10 meter, you should multiply the 20 into 10 by span, if you remember. So 20 into 10 by 10, 15, you cancel everything, you will get depth as a 1 meter. You understood? When the span length is very high, depth will obviously increase. So depth is 1.125 meter. Okay. So next question, you can pause and solve or you can check the answer later. The maximum permissible deflection effect, they have given a cantilever beam of 10 meter span. After erection of, oh no, they are asking maximum permissible. How much is the maximum permissible deflection of the cantilever beam? Okay. After the erection of the partition wall, means after the construction is over, they are asking. Okay. So we know deflection should not be greater than span by 350 or 20 mm after the construction. Okay, so what is the span? They have given 10 meter, so 10,000 divided by 350 is 28.6 mm, but we know span by 350 or 20 mm, whichever is minimum, so we will take the 20 mm as a deflection, maximum deflection allowed for that particular beam. Okay, so yes, we have reached the end of the document. Thank you for this chapter. If you want more problems, you can ask me, mail me. I will solve more problems and attach another video. So we will see in the next chapter. Thank you.